Hello, and welcome to Summer 2021 at Everett Community College's Advanced Manufacturing Training and Education Center. My name is Dane, and I will be representing Team 1 of the Engineering Tech 196 Advanced Workbenches with CATIA 3D Experience. Our goal was to highlight our ability to use kinematics, Knowledgeware, sheet metal, stress test, and prismatic machining. Our team of 6 each created a part or subassembly that utilized one or more of the aforementioned workbenches. Then we assembled them into this functioning model of an automotive lift. I hope you enjoy our presentation. As you can see, we got pretty complex motions in our kinematics. We have everything from prismatic and ruled directions to revolute and angular constraints. Our elevators move up and down, while the arms come in and extend out. And it may be hard to see in this view, but the handle is also moving up and down. The one on the hydraulic pump. Our group thought it was pretty fun to watch it move up and down to see all our hard work in motion. One of the great things about our model is just about everybody was able to use Knowledgeware. Some took it the extra step and made design tables that allows for different configurations. This quickly and easily changes configurations, showing the different combination of spacers that could be applied in the foot to achieve different heights. Some use Knowledgeware outside of a design tree, which allows us to edit any parameter on the fly. While it may look like parts of the model are left unaffected, due to the methods that were utilized in building this model, when you change one and update the assembly, you end up with a fully corrected model. This demonstrates proper use of Knowledgeware, as well as understandings of the way the system works. This arm is a nice transition into sheet metal, because the sheet metal workbench was used to create the support here on top of the arm. As you can see, we input our thickness and our desired bend radius. Once those are input, you can create a wall, and we used here 2 wall-on edges with bend to get the next support and the next welding area. It looks like some fillets were added along the edge just to keep the metal from being sharp and cutting anyone. An extra step for an extra model. As you can see, sheet metal was also used to create the drive-over ramp, which allows electrical components or hydraulic lines, whatever may be necessary, to be ran under or between the lifts without being damaged by cars as they drive on. Here, the teammate again defined the thickness of material and his bend radius, then created a wall or the primary or starting point, and added a flange on either side to create this nice curve. One of the most fun and also more difficult components of this project was stress testing it. As you can see, we created a static model and applied forces on it. We are applying force to each of the endpoints where the pads would go, and it's locked down along the end posts and the center support. As we add force, you can see through the von Mises stress test which joints take the most load. Displacement shows how far things are moving out of their original location. Deformation, while the color unfortunately doesn't show, shows things moving. There's a variety of different ways you can look at a stress test. Each tells you different bits of information, and together you get the whole picture of how the operation works under load. One unfortunate thing we ran into with running a stress test simulation in a student model was that we are limited on the size of the model you can run. As the model is converted into a mesh to do the simulation, triangles are computed for each curve, angle, face, whatever you have. And unfortunately, we can have only so many. So we were only able to stress test 8 out of our 40 parts, which, while still interesting and still providing a lot of information, unfortunately, it was not a complete test. Some of our parts required machining to complete. Here, we machined a plate, which is used between the hydraulic pump and the upright to allow for some offset. First, we ran the part through a facing operation. It took 2 layers or 2 passes to remove all the upper material. Next, a tool change and a periphery cut to mill down the outer edges to get it down to full size. Then, we pop some holes in it so we can run some bolts through it and mount the part. In the end, our team spent an enormous amount of time working on this project. We communicated well as a group, and we got the project done efficiently and correctly. It was a great experience to get to work with these guys and to come up with a model so complex and so interconnected. I think we all learned a lot and we all enjoyed our learning experience this summer at EMTech. Thank you for watching. We hope you enjoyed our presentation.